Graphing reciprocal functions. A reciprocal function is one written in the form y equals 1 over the function of x. On your CAS, graph y equals 9 minus x squared and y equals 1 over 9 minus x squared. So we've got y equals f of x, y equals 1 over f of x, and you can observe the following. Well, before we do any observations, let's get a picture of those two graphs here. The blue one is the y is 9 minus x squared, and the red one is the y equals 1 over 9 minus x squared. There's a few things we'll note, and then we'll come back and make our observations over here. First of all, we can see y equals f of x has a root, crosses the x-axis just here. And at that point, the reciprocal graph has a vertical asymptote, which we can see with the dashed line. And the same over here with this root. So this root of the blue curve, the red one has a vertical asymptote. Where f of x has a maximum, so here, the reciprocal graph has a minimum, down here. When f of x tends to negative infinity, so f of x is tending to negative infinity down here and again down here, the reciprocal graph tends to 0 from below. So we can see that the axis is a horizontal asymptote, and the asymptote is being approached from below. So those are some specific observations about this particular case. So general observations. When the original function passes through the x-axis, the reciprocal function has an asymptote, and we mean there a vertical asymptote. So whenever the original function crosses the x-axis, then the reciprocal function would have a vertical asymptote. As the original function gets larger, the reciprocal gets smaller, and vice versa. We saw on the graph over that when the original tended down to negative infinity, then the reciprocal tends to 0 from below. If we had the f of x tending to positive infinity, then the reciprocal must tend to 0 from above. So it would approach the axis but coming downwards. For y equals 1 over f of x, y equals 1 over f of x has poles where y equals f of x has zeros and vice versa. So we've just discussed that, poles meaning vertical asymptotes, so that's at points like this. Now if it was the other way round, and it was the y equals 1 over f of x, which had a 0 here, then the original f of x function would have a pole, or a vertical asymptote. Y equals 1 over f of x has a relative maximum, where y equals f of x has a relative minimum. So we saw that the other way around, where f of x had a maximum, and then the 1 over f of x had a minimum at the same point, and of course that works the other way around as well. So if we have a minimum for the original f, then there'll be a maximum on the 1 over f of x at the same time. Now if a, f of a, lies on y equals f of x, then a 1 over f of a lies on y equals 1 over f of x. It's fairly obvious that when the x-coordinate is a, the y-coordinate on f is f of a, and since we're doing 1 over f of x, the y-coordinate here would be 1 over f of a. As I say, it's obvious, but actually getting a few points can help us with a sketch. Y equals f of x and y equals 1 over f of x meet on the lines y is positive or negative 1. This is reasonably straightforward again. If you think about y equals f of x, if there's some particular value a such that f of a is equal to 1, then we have the point a1 on y equals f of x. But 1 over 1 is equal to 1, and therefore a1 must also be on y is 1 over f of x. So the graphs will cross when y is 1, and by the same argument when y is negative 1.